Okay, in this video we're going to be using second derivatives to find relative maximums and minimums. So we've learned how to take derivatives, but you can actually take second derivatives. So the notation for second derivatives would be f double prime of x, or this here, this d squared y over dx squared. So either one. If we have f, we'll say f double prime, and if we have y, we'll use this. Okay, now, there's another thing other than just relative and maximum and minimums. On a graph, you can have what's called a point of inflection. The function f of x is going to have a point of inflection, which means it changes concavity if f double prime changes sign. So concavity would be like this here would be concave up, and this one would be concave down. So if a graph changes from being concave up to concave down, or concave down to concave up, it has to change signs for the second derivative. The second derivative will change signs. Okay, and that's good to know, and we'll talk about that in the future, but right now we're going to focus on how to use the second derivative to determine where we have relative maximums and minimums. So using the second derivative to determine the maximum and minimum and what's located there. All right, so what you're going to need to do is you're going to need to take the second derivative. But if f double prime of x, which represents the second derivative, is greater than 0, which would mean positive, if I plug in a value and it's positive, then f of x is concave up in that situation. And remember, concave up looks like this, which would mean in that area or at that stationary point that I'm going to plug in, I'm going to have a minimum. You can see that. So if it's concave up and the second derivative is positive, I actually have a minimum. If f double prime of x is less than 0 or negative at one of my stationary points, then f of x is concave down, which, remember, would look like this. And then in that situation, if it's concave down, I can't have a minimum there. I'm going to have a maximum. Okay, so you just need to kind of know those rules or understand and be able to sketch your graph. Let's look at an example. So here I have y equals x to the fourth plus x to the fifth. And the first part here is just asking me to find the first derivative and the second derivative. So we know how to do that. We're going to say the first derivative, and we're just going to take the derivative of this. So dy dx equals 4x cubed plus 5x to the fourth. And then we're going to go ahead and take the second derivative. Yeah, we're going to take the second derivative, which I just take this first derivative that I had, and I take the derivative again. So 3 times 4 is 12x squared plus 20x cubed. Now, we know that we can use this first derivative and actually do a sign chart to figure out where I have a maximum or a minimum, if I have a maximum or a minimum. But in this case, I was actually asked to find the second derivative anyway. And if that's true, then I can use the second derivative to figure out the nature of the stationary points. Now, the thing about that is I still need to find the stationary points. And we know that to find stationary points, we set the first derivative, always the first derivative, equal to 0 and solve. And so in this case, I can pull out an x cubed as a greatest common factor. And then I'm going to have 4 plus 5x, and so I get x equals 0 and x equals negative 4/5. So that's what I get for my x values of my stationary points. Okay, if I needed to find the y values, I'd plug back in here. But I'm just going to leave this for now. Now that we have these, you can actually take the second derivative to determine, or potentially determine, their nature. So I have the second derivative here. I'm going to do this one first, this negative 4/5. If I plug in negative 4/5 to this second derivative, I get a negative value. I get negative 64 over 25. I don't really care about the value. I care the fact that at this stationary point, the second derivative is negative, which means at this stationary point, I have to be concave down. And so I have to have a maximum. So I know that this is going to be a maximum. Now, if I plug the 0 in, actually get 0. And we don't like 0 because I can't actually use this to figure out concavity because it has to be positive or negative. So in this case, I'd have to go back to this x equals 0. Okay, and I technically have this negative 4/5 over here, and I would have to test the left and the right of 0. Now, I don't have to worry about going any farther to the left of negative 4/5, but I would need to test to the left and the right here. And so if I do that, and I plug in like negative 1/5, I'm going to get a negative value. And if I plug in something over here like 1, I'm going to get a positive value. And so you guys know that this goes from decreasing to increasing. And so at this point 0 here, I have a minimum. So with the second derivative, if you plug in your stationary point and you get a negative, then it's concave down and you have a maximum. But if you get a positive, it would be concave up and you would have a minimum. But in this case, if you get 0, you have to go back to your sign chart right here. Okay, you have to go back to the sign chart to figure that out. Let's look at another example. Okay, so we have f of x equals 2x cubed plus 3x squared minus 12x. Again, we're asked for f prime and f double prime. So f prime of x equals 6x squared plus 6x minus 12. And we can find the second derivative by just taking the derivative of that, which is going to be 12x plus 6. Now, I do need to find the stationary points first. And I know this is stationary points, and so you should be finding your x and y value, but for us, we're just going to use the x coordinates of the stationary points at this time, okay, for this video. So I need to do that and determine their nature. So I'm going to set this equal to 0. This first derivative, always the first derivative, never the second for stationary points. And let's see, I can take out a 6. And I can factor this. So I get x equals negative 2 and x equals 1. Now, again, you can do a sign chart like normal and figure out whether you have a maximum or a minimum at these points. But since we have the second derivative anyway, I can just take this second derivative and I can plug in this stationary point, or this x coordinate of the stationary point. And when I do that, I'm going to get negative 24 plus 6, which is going to be negative. And so that tells me I'm going to be concave down. And so obviously you can see if you draw this, you have a maximum. So I have a maximum at that point. And then I can take my second derivative and I can plug in this x equals 1. And I get a positive value. So it's going to be concave up. And again, it's a good idea to sketch this graph and then to see here that you have a minimum, because a lot of people see this plus and they accidentally tell me that it's a maximum. That's not what it means on the second derivative. If this is plus, your graph is concave up in that area, and so the stationary point is a minimum, and vice versa, okay? All right, I want you to take a minute and I want you to try this problem. Okay, so again, we're asked to find f prime and f double prime. So f prime is equal to negative 4x cubed. F double prime is equal to negative 12x squared. I need stationary points, or in this case, the x values is what we're going to find of the stationary points. So I set the first derivative equal to 0. And obviously I can divide by negative 4, but I'm just going to get 0 equals x cubed, so x equals 0. That's my only stationary point. Now, if I plug that into my second derivative, I get 0, which means that doesn't help me. I need to go back to a sign chart just like normal, and I need to test values. So if I plug in a negative 1 here, I'm going to get a positive. And if I plug in a positive 1, I am going to get a negative. Okay, so this goes from increasing to decreasing. And so you can see that at x equals 0, we have a maximum. So in that case, the second derivative didn't really help me at all. Okay, so I want you to take a minute and pause the video and try this problem. Okay, so we have y equals x cubed plus 12 over x. So we're going to rewrite that as y equals x cubed plus 12x to the negative 1. Okay, and now we're going to take dy dx, the first derivative. So dy dx equals 3x squared minus 12x to the negative 2. Now I'm going to leave it like that right now while I take the second derivative. And when I do that, I'm going to get 6x plus 24x to the negative third. Okay, now that I have those two derivatives, I need to find the stationary points, which again, you always set the first derivative equal to 0 to find those. But when I do this, I'm going to write this as 3x squared minus 12 over x squared so that I can do the math with it a little bit easier. Let's see, it doesn't really matter how you want to do this. I can multiply everything by x squared to clear the denominator, which is going to give me 0 equals 3x to the fourth minus 12. And I can move my 12 over, divide by 3, and when I go to take the fourth root of this, I'm going to get plus or minus, and I'm going to have 1.41. So I'm going to have plus or minus 1.41 when I solve that. Now, I have the second derivative, and the second derivative I'm going to write again without this, so I'm going to test these values. 6 times 1.41 plus 24 over, and I'm just going to write this on the bottom, but I'm going to have 1.41 cubed. Now you should be able to look at this. With this positive here, this is going to be positive, this is all going to be positive, and so this is going to give me a positive value, which means at positive 1.14, I'm going to be concave up, which means I have a minimum. So at x equals 1.41, it is a minimum. I have a minimum there, okay? Then I'm going to take the second derivative and I'm going to plug in negative 1.41, my other stationary point. And again, since this is cubed, when I cube a negative, I still get negative. So positive over negative is going to be negative. And then I'll have a negative here. So I'm going to end up with a negative, which means I'm going to be concave down. And I'm going to have a maximum at negative 1.41. But you can, of course, type all this into your calculator to verify. Okay, take another minute, pause the video, and try this problem. Okay, so f prime of x is going to be 6 minus 2x. F double prime of x is just going to be negative 2. Okay, so let's look at this for a second. We still need to find the stationary points, and again, on this video only, we're doing just the x coordinates. So I'm going to set the first derivative, always the first derivative, equal to 0 to find stationary points, and I get 2x equals 6, and x equals 3. That's my stationary point. Now, guys, there's no x on my second derivative. My second derivative is always negative, because I have nothing to plug in there, so it's always going to be negative, which means my function f of x is always concave down. And so this, if this is concave down, this is going to be a maximum. So that one was nice. I didn't really have to do a lot. And you should recognize that, guys, because this is quadratic, and because of that, it opens down. So we kind of knew that anyway. But that's what happens when your second derivative is constant and it's negative, okay? Okay, I want you to take another minute, pause the video, and try this one. Okay, this one's not too bad. F prime of x is going to be 8x, and f double prime of x is going to be 8. So again, I need to find the x values or the x coordinates of the stationary points, so 0 equals 8x. So x equals 0. That's my stationary point. And because this is always positive for my second derivative, it can't change. There's no value, there's no variable to plug in next to it. Always positive, so f of x is going to be concave up. It's going to look like this for all values. So this must be a minimum. Okay?